In this video we discover the ray and the line equations, and firstly introduce an augmented vector which helps to handle translations in vector math. In game development, rays and lines allows for object picking and collision detection. Hi, my name is Alex and this is another video in the series about math for coding with vectors. First, let's start with a ray. A ray has an offset vector O and a direction vector R. R can be scaled. Usually, the coefficient is denoted as lambda. Adding O and the scaled R together, the ray can take on any point on the ray. Usually, the ray's direction vector is normalized. A line is represented by a normalized normal vector n. Similar to a ray, a line references any point P in space implicitly by measuring the distance of the point P to the line. This is done by using the scalar product of the normal n and a point P. So if the distance to the line equals 0, point P is positioned on the line. Any value other than 0, the point misses the line. This form of line equation is also called the normal equation of the line. By measuring the distance to the line, we can get another property of the point with respect to the line. The line cuts the space it is defined in two half spaces. That is the positive and the negative half space. If the distance of the point to the line is positive, the point is said to lay in the positive half space. If the distance is less than 0, the point lays in the negative half space. Let's say we want the line to be defined at a distance d away from the origin. Now we could measure the distance of any point in the space to that displaced line by simply subtracting that distance d from the distance of any other point measured. But how can we remember the line's distance d? We can do this elegantly by introducing an augmented vector. That is, the distance dn we want the line to be defined is placed in an additional component of the normal, but negated. So the normal becomes a 3D vector defining a 2D line. On the other hand, any point that needs to be tested against that line needs to be a 3D vector too, by introducing a 1 as an additional component. So by performing the scalar product, the distance d the line is away from its origin is subtracted from the distance the point is relative to the origin. This way we measure the distance d to the offset line in space. Note that if we want to test a direction vector against the line, we can simply zero out the third component, so the distance dn is not considered in that equation. Finally, say we have a ray and we would like to convert it into a line equation. We could do so by first constructing a normal nr to the ray's direction vector r by orthogonalization. The side the normal is facing is not important because the ray does not impose the concept of half spaces. So we can choose the side in which we would like to orthogonalize. The normal now represents a line through the origin. Now we would like the line to be an offset d away from the origin. This is simply done by using the offset vector O from the ray and measure its distance so we can construct the augmented normal vector. The augmented normal now carries the negated scalar product of the ray's offset vector O with the orthogonal normal nr. In this video we learned about the ray and the line equations. We will use those equations in later videos about collision detection in 2D games. Until next time, stay safe, bye now.